This video is about Mel spectrograms and MFCC algorithm, about their nuances and details of their implementation in different frameworks, the most popular frameworks and libraries used in the state-of-the-art audio processing frontends. For many years, MFCC has been the main algorithm for audio feature extraction. And even now, with the advent of deep learning, where the feature engineering process is often eliminated, MFCC and Mel spectrograms are still an important part of audio processing models. Feature extraction means that we are representing the audio signal or audio waveform in alternative space, the feature space. And MFCC is essentially the very compact and efficient representation of the frequency content of the signal. And Mel spectrograms are just signal spectrograms reorganized in Mel frequency bands. So if everything's so good with these techniques, why do I do this video? The main problem with MFCC is not the algorithm, which is quite straightforward. The problem is the variety of not only frameworks, but also the MFCC standards, so to speak. And these standards are reflected in different variable parameters of the algorithm. I give here for reference some well-known libraries written in C++ and Python, like Kaldi, HTK, librosa, torchaudio. And here's the example of the first 5 MFCC coefficients computed from the same signal at the same time position using each of these libraries with their default parameters. And as we can see, the discrepancies are significant. And in practice, there may be the situation when you have a dataset of MFCC vectors obtained in one particular framework, and during online audio processing, you use another framework that will give you different results, and the machine learning model will not work well. So we need to know how to unify this initial MFCC settings in all libraries. Also in .NET, there's an NWaves library. It provides the special MFCC extractor class, and it's very flexible and customizable. So you can specify any MFCC settings and get the results identical or at least very close to the results of the widely used frameworks. But anyway, we need to understand the meaning of all parameters in MFCC setup. Let's recap the MFCC structure. Essentially, it's about 4 steps or 4 building blocks. We compute the spectrum, we apply the Mel filter bank, we apply some nonlinearity, and we perform the discrete cosine transform in the end. There are also pre-processing and post-processing stages, and I will talk about them a bit later. So we have this pipeline, and how do we carry out these operations when we have the entire signal? We decompose our signal into frames, and these frames are relatively short. For example, in speech processing, the frame length is about 25 or 30 milliseconds. And we compute the MFCC vector inside this frame. Then we do the shift, and the hop length is usually not equal to the frame length, so frames usually overlap. And we compute the second MFCC vector, then we do the shift once again, and we compute another MFCC vector, and in the end we will have the sequence of these MFCC vectors, and we can call this sequence MFCC gram or a feature gram. Now let's talk about each of these blocks more in detail. So the spectrum block, we do the fast Fourier transform in the frame of signal. Fast Fourier transform is a complex operation, so we will have complex values. We discard the phase information, we get the magnitude spectrum, so by taking the absolute value of the complex numbers. But usually we compute power spectrum. So we can see already that we have at least 2 possible options here. But not only these 2 options, because we also can normalize each sample by the FFT size. This normalization will not affect much the ultimate MFCC vector. It will change only the very first coefficient, because this first coefficient reflects the frame energy. However, we have here 4 options. So now that we have a spectrum, what do we do next? We apply the Mel filter bank By applying the filter bank, I mean that we multiply each spectral sample by the weight of the Mel filters. And the problem here is that we have two main standards of Mel filter banks. The first standard is, I call it the standard Mel scale. It's used in HTK. It's the overlapping triangular Mel filters. And there's another kind of a filter bank suggested by Slaney, and it looks like this, and normalization is also different here. And also the number of filters is variable because in standard HTK filter bank, we usually have 23, 24 filters, and with this Slaney option, we have 40 filters usually. And also the frequency range can vary. So by default, it covers frequencies from 0 to half of the sampling rate, but we can customize it as we want. Then we apply the nonlinearity. And usually it's a logarithm operation, but logarithm can be different. It can be the natural logarithm, it can be logarithm 10. In librosa, decibel formula is used for some reason, i.e. 10 times log 10 x. And in some papers, cubic root is suggested, but it's quite rarely used. Usually it's a logarithm. Usually it's a natural logarithm or decibel operation like in librosa. What next? And then we perform the discrete cosine transform. DCT can be of type 1, 2, 3, 4, normalized and not normalized, but most often DCT type 2 normalized is used. So let's sum up. librosa. We compute the power spectrum. We apply the Slaney filter bank. By default, there is an option. We can use HTK, but by default, the Slaney filter bank is used. We apply decibel nonlinearity, and then type 2 normalized discrete cosine transform. Kaldi HTK, power spectrum, HTK filter bank with no alternatives, natural logarithm, type 2 normalized DCT. Torchaudio, power spectrum. Torchaudio actually tries to mimic librosa. So nonlinearity is decibel, like in librosa. However, the default filter bank is HTK, although in latest versions of torchaudio, you can also specify Slaney, but by default, it's HTK. And finally, there is also this Python speech features project. It's used by beginners and maybe by engineers, by other engineers, but anyway, it's quite popular. So the spectrum is power spectrum normalized. HTK filter bank, although the computation routine is slightly different, very slightly different, but essentially it's HTK filter bank, then the natural logarithm nonlinearity, and DCT type 2 normalized once again. So as we can see, the defaults in all these frameworks are different, and that's why we have different results. So now let's say a couple of words about the pre-processing. At this stage, we can do these three operations. All of them are optional, like mean subtraction. So we subtract the mean value of samples from each sample. And actually, this mean subtraction is available only in Kaldi and HTK, but anyway. Then there's a pre-emphasis, and pre-emphasis, at this stage, we apply a simple FIR filter with alpha coefficient, and this pre-emphasis coefficient is usually 0.95, 0.97. And we can also do the windowing, i.e. we can multiply each sample in the frame by the sample of the windowing function, and usually the Han window function is used. At least this function is used by default in all of the frameworks mentioned above. And the word of caution, in Kaldi and HTK, all these 3 actions are done per frame, on a per frame basis. And in NWaves, in .NET, in NWaves library, there is no mean subtraction in a general feature extraction routine. So if you want to mimic Kaldi and HDK behavior with this option on, in NWaves, you will need to use MFCC extractor Kaldi subclass. In all other situations, you will be just okay with the MFCC extractor class. So just a word of caution. And finally, what about the post-processing? So we already have the MFCC vector. What can we do with this MFCC vector? First of all, we can do the liftering, i.e. we can multiply each coefficient by this guy, where N capital is the lifter size of, or a size of a liftering window. Also, we can replace the first coefficient with the exact value of logarithm of the frame energy. As I already said before, the first MFCC coefficient anyway reflects the energy of a frame. But if you want it to be the exact value of log frame energy, you can specify append energy true or include energy true. So set this option to true. And finally, we can also add deltas. We can extend our MFCC vector with the first and second derivatives. For example, if we had 13 MFCC coefficients, after adding deltas, we will have 39 coefficients in our feature vector. And what about Mel spectrogram? So if we look at this pipeline of the MFCC algorithm, we will see that the Mel spectrogram pipeline is quite similar. We just discard this last stages, this discrete cosine transform stage, and nonlinearity becomes optional. Well, actually, Mel spectrogram is just getting the spectrum and applying the filter bank. And if we apply log nonlinearity, then the Mel spectrogram will be called log Mel spectrogram. So basically that's it. So we can also say that MFCC is the Mel spectrogram with discrete cosine transform applied to the result. Now we'll compare NWaves MFCC extractor with extractors from other frameworks, and we'll take a look once again at all these MFCC settings and parameters. For this, I have opened my application. It's called NWaves.Playground. It's the .NET Core Blazor application, so please welcome. I'm going to open a WAV file right now. So here it is. We see the audio waveform, we see the spectrogram, and here we can see the MFCC tab, and there's a combo box with MFCC settings. By default, it's a custom settings, so we can customize everything like number of MFCC coefficients, window type, preemphasis, and all these. We can see once again all these stages. The type of a spectrum, power, magnitude, normalized, not normalized, Mel filter bank, nonlinearity, and so forth. So let's choose the Kaldi standard. We can see that, and it will load the defaults for Kaldi. So the spectrum is by default the power spectrum. Mel filters is the HDK filter bank with 23 Mel filters. Nonlinearity is fixed. It's a natural logarithm, so we cannot do anything with it. It's not customizable in Kaldi, so it's fixed here. And let's take a look at librosa, for example. So the librosa defaults are Slaney filter bank with 40 filters. Nonlinearity is to decibel, and it cannot be changed as well. And let's get back to Kaldi, for example, and let's try to compute MFCC vectors. So I click compute, and we see the vectors. And I have also added pretty convenient functionality to this application of showing the analog Python code. So we're going to click this button, show Python code, and we see the code from Kaldi. So copy the clipboard, okay. And I'm gonna open the Jupyter notebook, and I'm gonna paste this code here, and let's run it. And we see the result, -29, -17, 0.17. So let's compare. -29, -17, 0.17. So we can see that the results are identical. And we can also do this with the librosa. Let's switch it to librosa. Let's compute it once again. We see the results are different right now. But once again, let's click the Show Python Code button. Now the code is different. Copy it to clipboard. Okay. And let's paste it to Jupyter notebook. And let's run it. And voila, we have the results for librosa. -234, 34, 11. And it's pretty close. It's very close. So, and the same goes for Mel Spectrogram. So you can use this application, this Blazor application, for interactive learning of the MFCC algorithm. And please enjoy. Finally, what about computing MFCC vectors online in real time? And for this, we will use the good old duo, NAudio and NWaves. NAudio will handle all these online audio capture, audio playback, and NWaves will handle the MFCC feature extracting itself. So let's just take a look at the code. I'm going to show you one possible solution how to do this. I have created an audio service class. And in this class, we have both capabilities for playback and for recording. And surely in your own project, you can extract two classes, one for playback, one for recording. So here we have the recorder and a player. And let's start with the recording functionality because it's done slightly simpler with NAudio. We create the wave-in object, we call it recorder. And when we initiate recording, here we create this object, we initialize it with some parameters, we initialize it with wave parameters, sampling rate, number of channels, the recording device number, and then we need just to subscribe to this event data available. So in this function, on recorded data available, we have our buffer in wave-in event arguments. So we have the buffer of new portion of audio samples, new portion of audio data. And we just run our extractor, our feature extractor from NWaves. It can be MFCC extractor, or in newer versions, in the newest version, it's the online feature extractor. We run the method compute from, and we pass this buffer. And voila, we have the vectors. We have newly computed MFCC vectors, and then we can do whatever we want. For example, here I invoke two methods, two events. But these events are just for my GUI, so that my GUI will update in my application. So simple as that. Now let's take a look at audio playback functionality. It's a little bit more complicated, but not really. First of all, we need to know what is iSample provider interface in NAudio. Our class audio service implements interface iSample provider. Actually, it implements iAudio service interface, but if we take a look at this interface, it extends iSample provider. I just add some convenient functions here for all audio services, but iSample provider defines two methods, actually one property and one method. The method read for working with online buffers of audio data. So how should we use this interface? When we do the playback, we create the player object and we create the source the source playback object that also in turn implements iSample provider interface. Like here, audio file reader, we load our file into this object, like here, reader, new audio file reader. And then we create the player object, wave out, and we initialize this player, and we pass this audio service object to this player, and then we need to override the read method. And in this method, depending on number of channel, I call read mono or read stereo. And for example, in case of read mono, we just need to read the data from a source iSample provider, and we fill the buffer here. And if we would write something like audio filtering, like audio filter, we could change this buffer here, and we would hear the filtered sound. But in this case, we don't do anything with this buffer. We just compute MFCC vectors from this buffer. We once again call this extractor compute from method, and we pass this buffer here. And we once again get this newly computed vectors. And once again, I raise this events. So that's basically it. It's pretty simple with NAudio and NWaves. We have extractor, we have iSample provider, a wave in, wave out, and the combination of these objects will give us the result. So I hope you found this video useful, and thanks for watching.